This is Dr. Hicks, and this is a video lecture for Chapter 18. We'll start off with a quick question, and like usual, the answers to these questions are in the back of the very end of the presentation. Most craters on the surface of the moon are believed to be caused by which of the following? Faults, asteroids, meteoroids, or volcanoes. So Chapter 18 is a bigger scope, and it's more about the universe. And what we're going to talk about are the sun, and then get a little bit more general and talk about stars in general and stellar evolution, and finally talk a little bit about galaxies. So when we're talking about bigger scale things like outside of the solar system, we need different units to kind of make these really, really big distances easier to handle. So one that we've already talked about is the astronomical unit, which is roughly the distance from the Earth to the sun. It's 1.5 times 10 to the 8 kilometers. But we're going to want to measure even bigger distances. So we define a light year as 9.5 times 10 to the 12 kilometers, and that is just how far light would travel in a vacuum in 1 year. A parsec is 3.26 light years. So that's also a very similar large distance measurement. Right, so let's talk about parts of the sun, because there's a lot of interesting stuff going around on the sun. So the chromosphere of the sun, so that's this outer part right here. It's just a layer of hot hydrogen gas that's about 25,000 Kelvin. It's kind of like the outer atmosphere of the sun. Now, the visible surface of the sun is the photosphere, and that's the more yellowy thing right here. So that's what we would consider to be the surface of the sun. And it's about 75% hydrogen, 25% helium, cooler than the chromosphere, but still really hot. 6,000 Kelvin is very, very hot. It has a granular appearance, and I will show you that in a minute. And it has a lot of interesting features like sunspots, there's dark black splotches, filaments, and prominences. Okay, so here is an actual picture of the photosphere of the sun, and it has like this granular appearance. These are convection cells where you have hot material rising, cooling, and falling, and you get kind of boundaries along the edges. Now, this dark area in the center is a sunspot, and it's about 1,000 Kelvin cooler than the sun around it, which is why it appears dark. And what's interesting is the number of sunspots rises and falls on regular 11-year cycles. And most likely they're areas of strong magnetic fields kind of trapping particles and causing it to cool down. So the prominences and flares are really cool surface features on the sun. So this prominence in this picture is an arc of hot hydrogen gas, hundreds of thousands of kilometers long. It would engulf the entire Earth easily. Now, associated with the sunspots are solar flares, and those are intense bursts of electromagnetic radiation. So here's another real picture of the sun, and you can see this big prominence. You can see filament, these long areas of cooler gas. These bright white areas are slightly hotter regions. So there's a lot going on the surface of the sun. So outside of that is the corona. And this is the very outer atmosphere of the sun, the crown, if you will. It is incredibly hot. much hotter than the surface of the sun. It's about 1,000,000 Kelvin. And most likely there are intense magnetic fields accelerating charged particles like electrons to really high speeds. And those are colliding with other gas particles and causing the temperature to be very hot. So, question 2, what's the temperature in Kelvin of the visible surface of the sun? And remember, the visible surface, that is the photosphere. So the really high temperature of the sun causes something called a solar wind. And there are electrons involved in the fusion process that's powering the sun. So there's charged particles associated with the sun. And that high temperature just kind of blows those charged particles out into space, and that forms what's called the heliosphere. It's kind of giant bubble of charged particles extending out from the sun and surrounding all of the planets. Now, lucky for us on Earth, since Earth has a strong magnetic field that deflects the solar wind away, and that's one thing that helps us hold on to our thick atmosphere. That's what having a strong magnetic field helps you. All the planets that have a big atmosphere tend to have a pretty strong magnetic field, and that's blocking the solar wind. Like I mentioned before, nuclear fusion is the process that powers the sun and all stars. And through a couple of different fusion reactions, we end up having 4 protons fuse together, and they form, so here's the 4 protons, 1 hydrogen. That's one way that you can write just a proton. So remember, this top one is the sum of the neutrons and protons. So if there's 1 proton, so atomic number 1, and the mass number is also 1, that means there's no neutrons. So it's just a proton. So if I can get 4 protons close enough together, they'll fuse into a helium nucleus. They will release some electrons. Sorry, these are positrons. It's an electron with a positive charge. These guys, this particle, that's a Greek letter nu, that's a neutrino. And this gamma, that's a gamma particle, so like nuclear radiation. And a lot of energy. So this is the fusion reaction that's going on in all stars. That means that the core temperature of the sun is super hot, about 15 million Kelvin. And this process that's going on is every second, 6 times 10 to the 11 kilograms of hydrogen, just hydrogen, is converted into almost 6 times 10 to the 11 kilograms of helium. So it's a huge amount of energy, 4 times 10 to the 26 joules every second. It's producing a lot of energy. Okay, so let's expand out and talk about stars other than our sun. And it turns out that most stars are actually part of a multiple star system. So unlike our sun, we just have a single star in our solar system. Most stars are part of a binary system, or possibly 3 or more equally, or 3 or more closely spaced stars. Binary star systems are the most common. Single star systems and 3-star systems are much less common. And the way that we're going to classify our stars is by brightness and temperature. So we'll start off with brightness. So when astronomers first decide to classify stars according to brightness, the brightest star in the sky was given a magnitude of 1. Higher magnitudes than that were dimmer. So a high magnitude star is dim. And that worked fine, but that didn't include other things that you could easily see, like the sun, the moon, or Venus. And all of those are much, much brighter than the brightest star. So if we put these things onto, like the sun, moon, and Venus onto the scale, it kind of breaks it. Plus, the magnitude scale didn't take into account how far away the stars were from Earth. So if you were an incredibly bright star, but you're real far away, you'll look dim. Same as a very dim star, but super close, could appear brighter. So these problems 1 and 2, the magnitude system didn't really take those into account. So if we put the sun, the moon, and Venus all onto this picture and take into account that our closest star, take into account that distance, we have to go negative to account for these brighter objects. So apparent magnitude takes into account distance and also includes the Venus and the sun and the moon. So a high negative number is a very bright object. Better way to do this is absolute magnitude. And that's the brightness a star would have if you put it 10 parsecs away from Earth. And this is going to put all stars on an equal distance footing, and it makes their brightness easier to compare. Now, when we bring color into the mix, we have to remember that longer wavelengths and shorter frequencies, so those are the same thing. Long wavelength, short frequency, the redder colors are cooler, but if you switch to short wavelength and high frequency, that's more energy, so those stars would tend to be hotter. So just by looking at the color of a star, we're able to get an idea of how hot it is. So I'll give you 4 colors. Which color star is the hottest? Red, orange, yellow, or blue? Question number 4. Which of the following distances is longest? 10 parsecs, 10 light years, 10 astronomical units, or 10 million kilometers? To give you a hint on this one, probably have to convert everything to a single unit system and then see which one is biggest. That's the surefire way to do it. Okay, so this all gets put together on something called the Hertzsprung-Russell diagram. And that's a way to classify stars according to their brightness and their temperature. So the vertical axis here, where it says luminosity, that's brightness. So the higher up you are on luminosity, the brighter you are. What is a solar unit? Okay, so a star with a brightness of our sun has a luminosity of 1. So this brightness scale is relative to our sun, right? If I draw a line straight across from 1, right, it goes right through the sun. That's our sun. Horizontal axis is temperature, and it's a little bit weird way to do temperature because the right side here is the cooler temperature, and as we go to the left, the temperature gets hotter. So these blue stars are really hot. These red stars at the bottom right are much, much cooler. And we can also, this also shows the relative size of the stars too. It's like these blue giants over here are really hot, they're really bright, and they're really big. really big because they've got a large size. So we can talk about the life cycle of stars, but it's different depending on how much mass the star starts off as. So low mass stars have a slightly different life cycle than high mass stars. So if we start off with a low mass star, it starts off as a protostar, moves on to the main sequence. So this middle line on the Hertzsprung-Russell diagram, that's the main sequence. It's where the majority of the stars are. Then it eventually turned into a red giant. So it gets real big in size, but it cools down because it turns red. And eventually it'll turn into a planetary nebula and possibly a white dwarf. So here's the star starting off as a protostar. So it's just a bunch of dust and gas. Eventually, under its own gravity, it can collect enough material that it collapses into a smaller and smaller, more dense area. And eventually, it can get dense enough in the protostar stage that it will start the fusion process and become like a real star. So when it's on the main sequence, that's when it's undergoing the fusion process, and that's where it spends the majority of its lifetime. Eventually, it starts to run out of fuel, and when it's a main sequence star, there's kind of two things going on inside the star. Like it's really, really hot, like 15 million Kelvin in the core. There's a lot of pressure that wants to make the star expand outward. But it's so dense because it has to be to have the fusion process start that there's a gravitational force holding it together. So there's a balance between radiation pressure pushing out and gravity pulling in. And when it hits the red giant phase, that balance is lost. And what you have happening is you lose the gravitational balance and the star can expand outwards. But as it does that, it cools down. And as it cools down, it changes color. So the red giants are much cooler than the stars on the main sequence. So what happens to that red giant? Two possible options. One is that in the core of the star, it eventually uses up all of the helium, the hydrogen in helium. So the fusion process changes. So slightly larger nuclei like carbon start fusing all the way up to iron. Once that fusion process uses up those heavier elements, it's kind of running out of steam. Then the outer layers get blown off. And so the outer layers of gas of the star get blown off. That's called a planetary nebula. And the hot core is called a white dwarf. In the white dwarf, there's no more fusion going on, and it's gradually going to cool down, and it's incredibly dense. It's almost like nucleus of an atom dense throughout the whole thing. So that means that they have such a high density that a teaspoon of white dwarf matter might weigh as much as 5 tons. Because they're not very bright, they're pretty low on a Hertzsprung-Russell diagram. That's what HR diagram is. So here's a picture of a binary star system, Sirius A and Sirius B. Here is Sirius B. It's a small white dwarf. Here is the Helix Nebula. This is a planetary nebula. The pretty colors in the ring is the outer layers of the red giant that were blown off, and the tiny white dot in the center is the white dwarf that's left over. Now, sometimes what can happen is the white dwarf can start gravitationally attracting more material, particularly if it's part of a binary star system. It can start like sucking off parts of its companion star. Well, when that happens, that can kind of start the fusion process over again and causes the star to explode. That's like so a nova, sometimes we just see a white dwarf suddenly get much, much brighter. It's an nuclear explosion on the surface of the white dwarf. Doesn't destroy the white dwarf, just it's not a new star. It's just a big explosion on the surface that makes it really, really bright all of a sudden. Okay, the second option for a low mass star is a catastrophic explosion called a type 1 supernova. And this happens with a white dwarf that has a carbon-oxygen core and that starts to attract enough new matter to become completely unstable. When that happens, that unstable core explodes in a highly energetic explosion. So elements up to iron are created in low mass stars through nucleosynthesis. That's how we get elements up to iron. Anything heavier than iron is created in a supernova, and it needs that intense of an explosion to force the heavy elements together into new, even heavier elements. So this is an artist's conception of a white dwarf taking matter from a companion star. That's what accreting means. Eventually, this white dwarf could turn into a supernova. So now let's look at high mass stars. So they're going to have kind of the same beginning. They start off as a protostar. When they join the main sequence, they're much hotter because there's more gravity pulling it together, and they burn hotter. That's got an important consequence because the hotter they burn, the shorter they last. So high mass stars have a much shorter life cycle than low mass stars. They will eventually turn into a red giant like the low mass stars did, but from there they can turn into a red supergiant, which is just like a red giant, only bigger. And the red supergiant can turn into an even more energetic explosive, which is a type 2 supernova. And the remnants of type 2 supernova are a neutron star or possibly a black hole. So here's a protostar on the left. It joins the main sequence as a blue star, so it's much hotter and brighter. Through the same process of using up all its fuel, it can turn into a giant. When that giant becomes unstable, it can expand into a supergiant. The collapse of the supergiant causes a type 2 supernova. And in the type 2 supernova, you have really heavy elements created too. The leftovers can be either a black hole or a neutron star. This says recycling down here at the bottom because some of this stuff that's blown off here forms the basis for new stars being able to form. So it restarts the life cycle of stars. So a massive supergiant, so a red giant has gone up to a carbon oxygen core. If it keeps on fusing past that and turns into an iron core, it will explode into a type 2 supernova. And this is where we get all the heavier elements, new material planets. So all this stuff where these new elements that are created, those are blown off out into space, ejected outwards. It's a catastrophic explosion. There's so much gravity left over that the protons and electrons collapse and turn into neutrons. And if there's enough neutrons, if it's enough mass, those neutrons can eventually collapse in on themselves to form a black hole. So a neutron star, the protons and electrons essentially fuse together to make neutrons and some other exotic particles like neutrinos. They make neutrons by effectively canceling their charge out as they fuse together. It's much, much denser than the white dwarf. White dwarf can still have atoms essentially in this atomic nuclei in the core. Neutron star, it's too much gravity and it's just like pure neutrons. So it's way, way more dense. A lot of them also rapidly spin and emit out radio waves that pulse in a regular fashion. That's one way you can detect neutron stars. They're not very bright at all. So this is an artist's conception of a black hole. That's got enough gravity that even light cannot escape. And Einstein would have explained that as the black hole bends space and time around it to such an extent that light cannot escape its gravity. So usually we talk about gravity acting on things with mass. Light doesn't have mass. How does that work? That's what Einstein kind of worked out with relativity, that his idea was that space-time is actually curved, distorted by massive objects. And light is following the surface of the space-time. It's kind of collapsed in on itself for a black hole. All right. What event is believed to create elements heavier than iron? Supernova, nova, neutron star, or accretion of matter into a black hole? Okay, last stop for chapter 18 is galaxies. And we're going to define a galaxy as a huge aggregate of stars, gas, dust, all held together by gravity. And these are kind of the fundamental components of the universe. If you zoom out of our galaxy, you're just going to see billions of other galaxies. And those galaxies, those billions of galaxies, are full of billions of stars themselves. Space is a big place. Okay, so Edwin Hubble, the person the Hubble telescope was named after, came up with a classification system for galaxies: elliptical, normal, normal spiral, barred spiral, and irregular. And these names are pretty much accurate descriptions of what these things look like. We've been able to identify several 100,000 galaxies. There's a lot of things to count. Astronomers estimate that there's billions of galaxies out in the universe. Most of them, just from observation, look like they're elliptical. For spiral galaxies, the regular or normal spirals tend to greatly outnumber barred spirals. And then irregular galaxies, which just don't have any normal shape, are only about 3% of what's out there. Right, elliptical galaxies are just a conglomeration of stars in an ellipse. So this is an elliptical galaxy, right in the center of the bright thing. No arms. Spiral galaxies have two well-defined regions, a central bulge, and then spiral arms coming out. The spiral arms contain a lot of stars too, but the bulge in the middle is where most of the stars are, packed tightly close together. Probably a black hole at the center holding all of that stuff together. Now, the closest regular spiral galaxy to Earth is the Andromeda Galaxy. And this is a picture of it. This is a barred spiral, and it's got spiral arms like the others, but it also has this bar feature across it. Then these are two pictures of irregular galaxies, the large Magellanic Cloud and the small Magellanic Cloud. They're galaxies in that they're clusters of stars, but they don't have any well-defined shape. So without any binoculars or telescope, you can see about 6,000 stars in the Milky Way. Estimate of how many there actually are is between 100 and 200 billion. And when we look into the night sky, sometimes you can see kind of a brighter plane that is looking into the galactic disk of the Milky Way galaxy. So we are out here in the Orion arm. And if you were to look, here's the sun. If you look inward, you would see something like this. So this bulge in the center is called the nuclear bulge. So this is the probable shape of the Milky Way galaxy just by doing a lot of observations towards the center of it. Okay, so this is a really good picture of the Milky Way galaxy taken by the Cosmic Background Explorer satellite. And it's kind of looking from our region of space towards the center of the Milky Way. And you definitely see a bulge in the center and a flat disk. That's a good sign that it's probably a normal spiral galaxy. So globular clusters are small globs of a few tens of thousands of stars, and those kind of form a halo outside the Milky Way. Back in the early 1900s, Harlow Shapley mapped out about 93 globular clusters and realized that our solar system was not the center. And that's important because that's kind of learning that we're not living in the center of the galaxy. We're out on an arm of the galaxy someplace. So he was able to guess or estimate that the solar system, our solar system, is about 30,000 light years away from the center of the galaxy. It's about 100,000 light years in diameter, but only 2,000 light years thick. And I know that these numbers make it seem like it's really thin. 2,000 light years is incredibly long distance. So it might be thin, but it's still really, it's really big. It's really, really, really big. And it looks like there's probably a very massive black hole at the core of all galaxies bulges. That nuclear bulge there's a lot of gravity there because there's probably a black hole holding everything together. All right, last question. What is the most abundant type of galaxy? Spiral, elliptical, irregular, or barred spiral? And this is the end of the chapter 18 video. Thanks for watching it. Most of this chapter is facts and how to classify things.